Have you ever wondered how a tiny atom can power an entire city? Nuclear power plants are incredibly efficient, generating vast amounts of electricity with zero greenhouse gas emissions. In this video, we'll explore how nuclear energy is produced, the step-by-step process of a nuclear power plant, and why it's both powerful and a subject of discussion. Nuclear power fundamentally relies on a process called nuclear fission. This is where a heavy atom, specifically uranium-235, is struck by a neutron. Upon impact, the uranium atom splits into two smaller atoms, releasing a tremendous amount of heat energy and additional neutrons. This single fission event can produce approximately 200 MeV of energy. These newly released neutrons then go on to strike other uranium atoms, initiating a continuous chain reaction. This reaction is meticulously controlled to ensure a steady and safe heat output. To transform this heat into usable electricity, a nuclear power plant incorporates several crucial components, each playing a vital role in the energy conversion process. At the heart of the plant is the nuclear reactor, where the controlled fission chain reaction takes place. Inside, fuel rods containing uranium are carefully arranged. Control rods, made of neutron-absorbing materials, are used to regulate the reaction by absorbing excess neutrons, preventing the chain reaction from becoming uncontrolled. A coolant, often water, circulates through the reactor core, absorbing the immense heat generated by fission. This heated coolant then transfers its energy to a steam generator. Within the steam generator, the hot coolant heats a separate supply of water, turning it into high-pressure steam. This steam is the driving force for electricity generation. The high-pressure steam is then directed to a turbine, causing its massive blades to spin rapidly. This mechanical energy is crucial for the next stage. Connected to the turbine is a generator. As the turbine spins, it drives the generator, converting the mechanical energy into electrical energy, which is then sent to the power grid. After passing through the turbine, the steam is cooled in a condenser, returning it to a liquid state. This water is then recycled back to the steam generator to repeat the cycle. Finally, a robust containment building, constructed from thick concrete and steel, encases the reactor. This structure is a critical safety barrier, ensuring radioactive materials remain isolated. Here's a step-by-step overview of how the entire working cycle flows, from fission to power generation. First, fission occurs in the reactor core, where uranium atoms split, releasing immense heat. This is the initial energy source. Next, the coolant absorbs this heat and efficiently transfers it to the steam generator, acting as a crucial intermediary. Inside the steam generator, water is heated by the coolant, transforming into high-pressure steam ready to drive the turbines. The high-pressure steam then rushes to the turbine blades, causing them to spin rapidly, converting thermal energy into mechanical energy. This spinning turbine drives the generator, which converts the mechanical energy into electrical energy, ready for distribution. Finally, the steam is condensed back into water and recirculated to the steam generator, completing the closed-loop cycle. Nuclear power plants are engineered with multiple layers of safety systems to prevent accidents and ensure secure operation. Control rods can quickly shut down the reaction if needed, and advanced coolant systems maintain safe reactor temperatures. The robust containment buildings are designed to ensure that radioactive materials are securely contained, preventing any environmental release. Nuclear power offers significant advantages: a huge energy output from a small amount of fuel, very low greenhouse gas emissions, and a reliable baseload power supply. However, challenges such as safety, radioactive waste disposal, and high construction costs require careful management and continuous innovation. Nuclear power exemplifies how advanced engineering can harness the fundamental building blocks of nature to power our cities. As technology progresses, safer and cleaner reactors like small modular reactors and fusion energy are becoming increasingly viable, promising a future of sustainable power. If you found this explanation helpful, please subscribe to Simple GaN, like this video, and comment nuclear energy below if you'd like a part 2 on fusion reactors.